Okay, so in this lesson, we're continuing with our first strategy for use substitution with integrals in calculus. And we're applying that strategy to integrals that contain trig functions. So in this first example, we see that we have an interior function. It's inside of the cosine function. And if we let u be equal to x cubed, then the derivative of u would be 3x squared dx, which we see that is on the outside of the function. So all of this is our du, and inside we'll replace that with u. So if we rewrite this integral, we get the integral of cosine of u du. Everything that was on outside of cosine is replaced by du. And again, the purpose of u substitution is to simplify the integral to a basic rule, a basic antiderivative rule that we know. And we know the antiderivative of cosine, and that's going to give us sine u plus c. Once again, this is the answer in terms of the u variable. We want to return it to its original variable. So we can say that replace u with x cubed. Our final answer is sine of x cubed plus c. Again, if we wanted to check this answer to see if it gives us back the original function we started with, we would use the derivative. We understand that the derivative of a constant is 0, so we don't even need to look at that part. But we look at the sine of x cubed. Remember, we have to use chain rule. So there's the outside function's derivative. The derivative of sine is cosine. We don't change the inside function, but then what we do is we take the derivative of the inside function to complete the chain rule. So the derivative of x cubed is 3x squared, and we see that this matches our original problem. So once again, the antiderivative of 3x squared cosine of x cubed is simply sine of x cubed. Let's look at this next example. Again, we look at the interior function. We say let u equal 2x. Then du is equal to 2 times dx. And we say, well, we have the dx, and we have an 8 out here, but we can split this 8 up into 4 times 2. And we'll group the 2 with the dx. So I'm going to rewrite this. So you see I broke up the 8 into a 4 times 2. I put the 4 on the outside of the integral. I grouped the 2 with the dx so that it matches everything I need for my du. Now I can complete the u substitution. And we see that the 2x has been replaced with u, the 2dx has been replaced with du. Now this matches a simple antiderivative rule. We know that the antiderivative of secant squared is tangent. So the 4 from outside the integral just multiplies tangent u and plus c. And we say, well, we don't want this to be in terms of u. We want to return the original variable, which was 2x. So our final answer is 4 times tangent 2x plus c. So in this one we had some rearranging. We had to break up that 8 into a 2 and a 4, group the 2 with the dx so we can match it up exactly with du, and we moved the 4 out front and multiplied it to our final answer. So this one here is a different type of substitution. Instead of the interior function being a function of x, the interior function is a trig function. So we can say sine of x is inside of the square root. So let u equal sine of x. Then du is the derivative of sine of x, which is cosine of x dx. So let me scratch this out. No adjustment is needed here because we have an exact match. So we can rewrite this as the square root of u du, where cosine x dx was replaced by du. Now we change the u to the 1/2 power, so we can use the power rule for antiderivatives. We add 1 to 1/2 to get the new exponent, that gives us 3/2. Dividing by 3/2 gives us 2/3 u to the 3/2 plus c. And now we want to replace u with the function it's equal to, sine of x. So our final answer is 2/3 sine of x to the 3/2 power plus c. So this was an example where the interior function was a trig function. So here's another one with 2 trig functions, just to get us to see this pattern. You can let u be either cosine or you can let u be sine. Now, if we let u be sine, it will be a direct substitution problem. No adjustment will be needed. But we just saw that in example 3. So I'm going to let u be cosine instead. Now the derivative of cosine is negative sine, and that's what is going to require an adjustment. I have a positive sign, so I need to multiply by -1. Well, +1 is equal to -1 times -1. So I would have to introduce both -1s in here, and one of them I would attach to the sign, and one I would put out in front of the integral. So I can rewrite So you can see I introduced 2 -1s being multiplied in, because -1 times -1 is +1. Then we didn't really change the problem. And I have the -1 times sine that I need to match up for my du. And now I can let cosine be u. And we say, well, if we rewrite this as an integral of u, here's the substitution step. We have -1 times the integral of u du. Again, the purpose of substitution is to give us a simple integral that we can evaluate. The antiderivative of u is 1/2 u squared plus c. Times that -1, we have -1/2 u squared plus c. And once again, we want to return this to the original variable. U is equal to cosine of x. And that would be our final answer